All right. How's everybody doing? Good. Nice to see everybody.
Me too.
This is my project. I decided to name him Johnny 3 Sensors just because he uses 3 sensors to sense his environment and navigate obstacles. My objective or vision for this project was to create this self-navigating robot. I wanted something that could navigate easily in and out of corners, get himself out of tight spots, and something I could just let go and have no problem moving around, not getting stuck anywhere. And I would say I would be moderately successful. And I wanted to do all this just using parts that anybody could find, either online or through other resources, and document the whole project so anybody else could do it. So why the need or interest in automation? Well, we could explore other worlds, we could automate labor, or just for fun, basically, as in my project here. So right now, I just want to introduce you to my Johnny 3. So you can see right there, he backed out of a pretty precarious little situation there.
That is cool.
I think right here he's gonna, oh, no. Oh yeah, he's gonna do a few donuts for some reason. Well, here's just a still picture of the project. As you can just move along to another view. Here's a overhead view of the entire project. I'll get into a little bit more about each the parts here in a second. So really isn't too much to it. I used the ARDUINO NANO basically because it's this microcontroller has a lot of resources available to it, and it's in a pretty small package. The ultrasonic sensors, which allow the robot to see. The motor driver, because you can't operate the DC motors off of the microcontroller. And of course, the 4 DC motors, the voltage regulators to regulate the power to the motor driver and the sensors and the microcontroller, and of course a 12-volt lithium-ion rechargeable battery. The chassis is two pieces of hard plastic separated by some spacers. I purchased this rather than trying to build something like this just because it was easier. It's pretty nice, but if I had a 3D printer, it would be fun to design your own, make it more customized. So the Arduino Nano, like I said, has a lot of resources. It has 30 pins altogether with 8 analog pins, 22 digital, 6 of which have the pulse width modulation capability. It has a surface mounted 16 megahertz crystal. And like I said, it's all in a small convenient package that fits easily onto breadboards and other prototyping platforms. And as you see, there it is in there in the circuit. The ultrasonic sensors, these are pretty cool. They have 4 pins. You have your power, ground, trigger, and echo pin. And it works by setting the trigger pin high for 10 microseconds, in which case it will send 8 cycles of a 40 kilohertz pulse. And then it, after it sends the burst, it will set the echo pin high until the return echo is received. As you can see in the graphic I have down here, it's a little timing diagram. The trigger is set high for 10 microseconds, in which case it'll send out the pulse. And then the pulse in is what determines the distance. It's proportional to the distance that was covered by the transmission and of the 40 kHz signal. And there's the 3 sensors mounted onto the front of the robot. And now I'm gonna speak to you a little bit about the motor driver. I use the L293D motor driver. And like I said before, the microcontroller cannot power the DC motors by itself. It has to have a motor driver to help it operate these wheels. So how it works is by setting the input either low or high or low, controls the direction that the wheels will rotate. And then by using the pulse width modulation on the enable line, you're able to control the speed. Controlling the speed this way allows for the maximum torque on the DC motors. If you were just to set a constant DC voltage and regulate the power by just adjusting it up or down, you would lose a lot of the torque of the motors and it wouldn't really be able to perform like you'd want it to. This particular motor driver can handle up to 36 volts on its VCC2, the motor voltage, and it delivers 600 milliamps per channel, which in my project wasn't quite enough for the 4 motors, so I ended up having to use 2. And you see, there's the 2 motor drivers in the circuit. And I just use regular DC motors. They're just simple, cheap, effective. I wouldn't expect them to last very long, but for the project, they worked out great. And the voltage regulators, I just used the L7800 series. I used one 5-volt regulator to for the ICs, the microcontroller, and the 3 sensors. And then I used the 2 8-volt regulators to control each motor driver. I had to use a heat sink because I was having trouble with the whole unit overheating, and then it wouldn't have any power. It just would lose power over. Without the heat sinks, it was about 1.5 minutes it could run. But once the heat sinks were attached, it had no problem running for extended periods. So this was the whole thing put together. As you can see, you have the 3 sensors connected to the microcontroller, a switch to turn it on and off, the 2 L293D motor drivers connected to 4 DC motors. This is the program flow chart. Basically, after you initialize, it's going to check to see if that switch is on or off. And when it's off, it's not going to do anything. But if it's yes, it'll start the program, in which case it'll take a reading from the front sensor. And then if the sensor is less than 5 inches, then it will just go right into a backward subfunction where it'll turn around. If the sensor was greater than 36 inches, it would just go forward. All clear, just go forward. But if it was, greater than 5 inches, but less than 36 inches, then it would go in and start looking at the left and right sensors and comparing those distances and making decisions based on what it sees there. So, if left is greater than right, it's going to go left. If right's greater than left, it's going to go right. If they're the same, it's going to turn around, go backwards. So I used the ultrasonic library, which had all the code of running the sensors, setting the trigger high for 10 microseconds, getting the pulse in, and then doing the math to convert it to either centimeters or inches. And that's all just initializing your pins and setting your variables. Right here, what's happening is it's just looking to see if that switch is on or off. If it's off, then it's just gonna stay stopped, not gonna do anything. Otherwise, if it's on, it's gonna start by reading that front sensor and heading right into the main program. So here you can see if it's less than or equal to the 35 or 36 inches, it goes into a nested if-else statement to start making its decisions on turning left or turning right. The delay here will control how far it goes, right or left. And then after each time, I put in this check distance all subfunction so that it would know, because after it moves, it's not going to be in the same position it was before, so it has to get those distances again. And here it just goes in. This was a neat command. I wanted to constrain the values for the backwards function because, if it gets down to a certain point, it doesn't really matter if it's 3 inches or 4 inches here. If it's seeing 5 inches all around, then it's time for it to back up. And then here are just the forward functions. If it's greater than 36 inches, it's going to go forward. And here's just a quick example of one of the functions here. This is setting the inputs for the right and left motor, low, high, so it spins in one direction, and setting the speed with the analog right value. Excuse me. So that's basically the project. What's next? Just kidding. While I was developing the project, I had a good idea to put bumper buttons on it. So if, in fact, it does run into something, it would just automatically back up, or stop because there's a hazard there. You don't want it just to try to, if anything goes wrong, to keep going forward. And, instead of using the 2 L293Ds, I wanted to upgrade the motor driver to something that could handle a little more current and power. I'd also thought about upgrading the sensors to either infrared or or a laser sensor. And there's a better ultrasonic distance sensor. The one I used was just the cheapest one. This one's just a little bit better, supposedly. And then always the program could always use a little bit more refinement and adjusting. So this project came with its fair share of troubles. One of the main issues I had was power. I didn't really realize how much power these four little DC motors were going to take. At first I was going to use 9-volt batteries, but that just did not provide enough power. So after trying a few things, I finally came up with the 12-volt lithium-ion power tool battery supply that has no problems powering this vehicle. And also with the power supply, I had a couple times switched the polarity on my voltage regulators, and that instantly fried them. Luckily, I had a few backups, so no loss there. And here's another video with some of the earlier trials. I think I'd gone through some 20 different program codes, just trying to figure out what's going to work best. Kind of just headed into this thing without knowing too much, and just trying out a few things, getting some ideas, seeing what works and what doesn't, and going from there.
Hey Nick, why did you choose the ultrasonic ping versus, say, a touch sensor or one of the Sony distance sensors?
Mostly because it was cheap.
Okay.
These sensors are less than $4 a piece, and I got a pack of 5 for less than $10. Worked pretty well. I'd gone through and actually used a tape measure and kind of like in a wooden board and kind of tested to see just how accurate they were, and they were returning pretty close values. Yeah, I just wanted something that could look out at some distance and kind of make adjustments.
Gotcha. Well, outstanding work. It's amazing to see these guys move around based on where you started and what it looks like today. So way to go.
So anyways, any questions?
Good job, Nick. Very good job.
Thank you.
Awesome, dude.
Great job,
Hey,
Nick. Nice job.
Thank you, Dave.